This is the third lecture on MOS amplifiers. We have another lecture on MOS amplifiers tomorrow. So hopefully we'll be done with the basic MOS amplifier stages after tomorrow here. And I'm going over it pretty fast because this is more like a revision. Counterpart of common emitter is common source, counterpart of common gate is common base, and similarly Cascode. So we have seen all of that. The analysis is very similar, and that's why I'm going over it pretty fast, because once you where the differences are in the DC analysis, the equations are a bit different. But once you go to small signal analysis, it's pretty much the same here. Okay, so let's start then. And last lecture we were seeing a common gate amplifier, and we had said that the common gate amplifier is not a very good voltage amplifier. The reason being is that the input resistance of this particular amplifier is pretty low. When you look into the source here, you see a very small resistance, and therefore if your input has a substantial source resistance here, most of the voltage that you see here will drop across this, and very little will go into the amplifier itself. So it's not a very good voltage amplifier. But we also saw that if instead of voltage as an input, you give current as an input, all right, which means that the input is a current source, meaning that the resistance RS is large. Okay, it's a current source input. Then what happens is, because the common gate amplifier input resistance is small, this entire current that you see here, instead of opting for RS, will actually flow into the common gate, into the source here. And once it flows into the source, you know that this AC sinusoidal current, once it flows into the source, it will flow out through the drain. There's no other path. It will flow out through the drain. And when we are talking about AC or small signal, it will flow out through the drain and go through RD. And note that this will be small signal ground, right? So it will start from here, go through the source, enter, and come out and go into the small signal ground here. So the voltage that you will develop is current IS times RD. Even after doing detailed analysis, this is what you would get from by tracing the path of the current here. And therefore, it's a very good current to voltage converter, the circuit. So so it's more like a transconductance amplifier, where the output is a voltage and input is a current here. And not a transconductance, but a transresistance. Voltage, if I look at voltage as an output and current as an input, so if you take the transfer function, it's voltage divided by current. So it's a transresistance amplifier here. All right. So just like in a bipolar, we can combine the advantages of a common source and a common gate amplifier. And so if we look at these two, what we see is that, as we said, common gate works very well with a current input. And common source, of course, is a voltage amplifier, works well with a voltage input. But if we look at this particular amplifier, we note that this common source stage is also a good voltage to current converter. If I look at my this common source stage part here, if I look at this particular node, drain node, then the whole thing that you see here looks like a current source in parallel with a large resistance here. So this one then can also be looked upon as a good voltage to current converter. So this one will convert it into a current like this. And now this current input can be given as current input to your common gate amplifier here. So what you do is you connect your common gate stage over here, and what you get is a new amplifier, which is a combination of common source and common gate. And this is what we call as a Cascode amplifier here. And the advantages of the Cascode amplifier are that the input resistance remains high because you're applying the input to the gate of the transistor here. And we'll just see the gain remains the same as this particular amplifier. Gain will be the same as a common source amplifier here. And frequency response will be improved. Okay? And we'll see why the frequency response will be improved in a little while here. So let's calculate the gain of this particular amplifier and confirm that the gain of this amplifier is nothing but same as gain of this amplifier, which is GM times RD. Okay. Now in that context, I had said that there are two very useful results. That if these are small signal results, that if you see a transistor with a resistance attached in the source, RS could be anything, it could be 0 as well. Then what you could do is you could build a Norton's equivalent at this particular node. And Norton's equivalent, as we know, will be a Norton's current and a Norton's resistance. And through small signal analysis, it's easy to show that the Norton's current is equal to GMVG, which is here, 1 plus GM RS here. Okay. And so that's for the same result applies for a PMOS as well. Although I'm deriving it for NMOS, note that the small signal model of an NMOS is the same as PMOS, and all the results are the same. And the Norton's resistance, which is the resistance looking from here, is R0, 1 plus GMB RS here. Okay, so that's one useful result. The other one is, if you have a transistor, you can build a Norton's equivalent at the source node also. And here again, IN and RN are there. IN is equal to GM times VG divided by 1 plus RD by R0. If RD is small, then of course you can neglect it and it's simply equal to GMVG. Note the minus sign here. And the other one is the Norton's resistance, which is resistance looking from here, which is equal to 1 by GM plus GMB, 1 plus RD by R0 here. So these are two very useful results, which we will use to derive properties of many amplifiers. Okay. All right. So I've kept these two results in the background here. And so let's calculate the gain of this particular amplifier. Now, one way, of course, is you go ahead, substitute small signal model of each one of them. You'll get a circuit, solve it, and you'll get the answer. Okay. The other way is to use these results here. Use these results and obtain the answer that you're looking for. So if we look at this particular amplifier, we note that if we focus on this part here, okay, if we focus on this part looks like this one here. Okay, so this whole part here, I'm not talking about this part here, from here down to here, can be replaced by a current source, Norton's value, current source, and a resistance. Okay, so at this node here, we have built a Norton's equivalent. Of what? Of which part? The lower part here. And so it's a Norton's current and a Norton's resistance here. What will be the value? Use this particular expression here. It says if there is no RS, the Norton's current is simply GMVG. So that's what we have put, GMVG. VG is nothing but VS here, or VS here. So, and what will be the Norton's resistance? Since there is no RS here, so Norton's resistance simply R0, so you put R0. All right. So this whole part here has been replaced by this one, by using this particular result. All right. Once we have that, then the next thing that we do is note that both these results that you see here rely on building a Norton's equivalent. So what we can do is note that if I'm interested in voltage at this node. So if I build a Norton's equivalent at this particular node, Norton's equivalent at this particular node means that the whole circuit, looking at it from that node, is a current source in parallel with RL. Okay, so let's do that. So this is the circuit here. I'm building a Norton's equivalent. Norton's equivalent means I have to find the Norton's current here. Norton's current you find by grounding and finding out what is the current that flows here. So now if I look at this one, the source of this particular current is obviously this one here. There's no other source. So now look at this particular current here. This current has two choices. It can either, don't worry about the direction. Direction is up, down, or whatever. It doesn't matter here right now. So this is the current here. The current has two choices. It can either flow through R01 or it can flow into transistor M2. All right. These are the two paths. Now, if I look into M2, if I look into the M2, what do I see? If I look into M2, note that this is ground. How much resistance do I see when I look into M2? Into the source. Go back here to this result. This resistance Rn is nothing but resistance looking into the source. And how much is it? 1 plus Rd by R0, because this is ground here. So there's no Rd. So the resistance looking into the source then becomes 1 by Gm plus Gmb. So now note that this current has two paths. It can either flow into M2 and it sees a resistance 1 by Gm plus Gmb, or it can flow through R01. Right? These are the two paths for the current to flow. And at this stage, you have to remember the relative magnitudes of the two. R0, a typical value may be 4 mega ohm, right? 4 mega ohm and in mega ohms, while this is in kilo ohms here. 1 by Gm plus Gmb is in kilo ohms here. So what happens is this current that you see here will bypass this one. A current always prefers the lowest resistance path here. So this current would entirely flow into M2 here. And as it flows into M2, where will it come out? It will come out through this particular terminal here. So IN then is equal to simply equal to GM1 Vs. So just by examination of the circuit, one can write here that IN is GM1 times Vs. That's it. So the Norton's current at this particular source is GM1 Vs. So we have found the Norton's current. Next thing is, let's find out the Norton's resistance here at this node here. Now, Norton's resistance, if you look at it, so forget about the ground now. There's no ground. So I'm asking what is the net resistance at this particular node. That will be equal to resistance looking up, which is RD, that's the first term, and resistance looking down. Now, when you are looking down, when you find Norton's resistance, what you have to do is, you have to short all the sources. Right? When you find a resistance, you have to short the source. So when you short the input source, Vs becomes 0. So this current is no longer there. So what is the resistance looking down? You can see here, this particular circuit here. What is the resistance looking down? It is R0, 1 plus GM RS here. So what is RS for this case? R01. So what is the net Norton's resistance? R02 here, multiplied by 1 plus GM2 R01 here. The reason why I have not included GMB here, all right, so in fact, one should, this is an NMOS, one should, for the sake of completeness, include GMB also. Okay, so it should have been R02, 1 plus GM2 plus GMB2 multiplied by RS. RS is nothing but R01. All right, so this is this particular resistor here. And note, RD, as I've said, most of the time RD is much smaller than R0. And in this case, RD is in parallel with R0 multiplied by a large term. If you multiply GM2 times R01, that term itself will be around 100 or so. So this whole resistor would be about 100 times R02. So it's a very large resistor, and you can neglect it in comparison with RD. And so therefore, the Norton's resistance at this particular node is simply equal to RD. Resistance looking up is RD, resistance looking down. Note that when we say resistance looking up, what we mean is resistance between this node and ground. And resistance looking down, again, resistance between this node and ground. And therefore, the two resistors come in parallel. Okay? So this resistance then is simply RD. Which means what? That at this node, then, we have a Norton's equivalent. That at this node, we have IN and we have RN. Right at this particular node here. Okay, so which means that the whole amplifier looks like a Norton's current and a Norton's resistance here. And therefore, what will be the output voltage V0? It would be simply IN times RN here. Okay, so the output voltage then, what you could do is after building Norton's equivalent, so the output voltage will be this current will flow through RN here. That's the only possibility, RN, and therefore the output voltage will be GM1 times Vs multiplied by RD. A minus sign will be there because the current is going to flow like this here, and this is the voltage here, output voltage here. So the output voltage then will be minus GM1 RD, and therefore the gain of this amplifier is minus GM1 RD, which is just like a common source amplifier. Okay. So in terms of gain, adding a common gate stage doesn't do anything. Whether you add it or don't add it, it's just the same as a common source amplifier with the gain GM1 times RD. Okay. So that's the, so note that how we arrived at the expression for gain. Wherever you want to calculate something gain, all that you do is, suppose you are interested in gain at this point. I will just do a calculation again. At this point, then what you do is you build Norton's equivalent at that point. At that particular node, build a Norton's equivalent, which means that the whole circuit, looking at it from this node, would be like INR. And then the gain voltage will be at that node will be simply IN times RN. So the entire small signal analysis boils down to basically at any point building a Norton's equivalent. And while you are building Norton's equivalent, these results that you see here, they are very useful. So you'll be either building a Norton's equivalent at the drain end, or you'll be building a Norton's equivalent at the source end here, and these two results will be very useful. Right? So either you'll be taking a voltage at the gate, or either at the drain, or at the source, and you'll be building Norton's equivalent. And therefore, these two results which you have already derived will be very useful for you. Okay? So once you memorize these two results here, after that you don't have to do a direct small signal analysis by substituting the model. Just use these two results here, and all the analysis you can do based on the basis, all, complicated amplifiers with 10 transistors and all that, which hopefully I'll show you later on, you can analyze just using these two results. Okay. So these two are very powerful results here. All right. As I said, we might be interested in building a gain at this particular point here. And the reason is, we'll soon see shortly, is that when you calculate frequency response, As I've said, to calculate frequency response, you need to identify all the nodes in the circuit. You need to calculate the time constants at each node. Now, when I calculate time constant at this node, I have to calculate the net capacitance at this node. And as you note, the capacitance at this node, there's one capacitance which is CGD, which comes here. And this CGD gets multiplied by the gain. And what is the gain that I'm talking about? Gain between this node and this node. Okay? And therefore, I need a gain between this node and this node also. Although my output is here, but to calculate the Miller's effect here, apply Miller's theorem here, I need a gain between these 2 points. Okay? So let's calculate the gain between these 2 points. Remember, we are building this Cascode amplifier with the hope that my amplifier will not suffer from Miller's effect. Right? So now we know that we have a large gain at this point. Between here and here we have a gain. Right? Depending on the value of RD, we can have a very large gain here. But this transistor suffers from Miller's effect due to gain between these 2 points. Now, if we can show that the gain between these 2 points is very small, then it means that my amplifier does not suffer from Miller's effect here. Okay? So that's why I'm going to calculate the gain between these 2 points. Okay? So the focus is now here. That's why I'm calling this as some voltage V01. Now, if you want to calculate the gain at this particular point, what you do is you build Norton's equivalent at that point here. So first thing is, note this whole part here that you see here, this whole part is replaced by GM1 VS R01, just as before. Okay? All right. And this is nothing but coming from here. Okay, so we have here. Now we want to build Norton's current here. All right. So I've skipped a lot of points, but let's see steps here. Let's see if we can understand here. So you want to build a Norton's equivalent at this point. How do you find Norton's current? What do you do to this node? Short it. Okay, short it to ground here. So take this node, short it to ground, and find out what is the current flowing into the ground. What will be the current? If you take this node here and short it to ground, what is the net current that flows through the ground? Well, there's only source here, GM1 VS, and obviously it's going to flow into the ground. It's not going to flow through R01 or anything else, right? So Norton's current is GM1 times VS. Keep that in mind, Norton's current here. What is the Norton's resistance here? Norton's resistance means resistance looking down, which, what do you see? R01. When you look down here, note that this current will become open circuit. To calculate the resistance, you have to short the source here. So you make VS equal to 0, this current is open circuit. So when you look down, you see R01. When you look up, what do you see? You look into the source here. So you use this expression. You use this expression, and that's what we have done. 1 plus RD by R0, GM plus GMB2. So this whole thing that you see here, R01 parallel this, is nothing but Norton's resistance at this particular node. Right? This whole thing, R01 parallel here, is Norton's resistance. And Norton's current is what? GM1 times VS. So what is the net voltage developed at this node? Norton's current multiplied by Norton's resistance, which is GM1 times VS multiplied by Norton's resistance here. And therefore, the net voltage will be, and the gain will be, if you take VS on this side here, the gain will be GM1 R01 parallel. Okay. So as I said, once you build a Norton's equivalent, your voltage at that particular node is Norton's current multiplied by Norton's resistance here. All right. So if we do that, if we look at this particular expression, R01 again is very large, so we neglect it. And RD in comparison with R02 is also small, so we neglect that also. So we get here gain, which is GM1 by GM2 plus GM2. And note that if both the transistors are identical, they are biased at the same current, so GM1 and GM2 are almost the same, and therefore AV1 is actually very close to 1. If you neglect GMB2, AV1 is actually 1 or a little less than 1. Okay, which means what? That although you're building a large gain between this point and this point, the gain between here and here is very small, and therefore any gate to drain capacitance here gets multiplied by what? By this gain, which is less than 1. All right, so we don't have Miller's effect between these 2 points here. Okay. All right. Okay, so let's take an example quickly and go through it. So we have this amplifier here. So this is biased at when you apply 1.5 volts to a transistor 2x1, you can easily calculate that in saturation the bias current is 25 microamperes here. Saturation voltage, because it's 1.5, is 0.5 volt here. We can calculate the DC value of this voltage here, V01. This comes from whatever is the voltage here minus VGS of this will give us the DC value here. And once we know the current multiplied by 80K gives us the drop here. So we know the DC value of this voltage here. Okay. Gain is nothing but, once we know the current, we know all the transconductance. Gain is GM times RD, which is minus 8 here. Gain between this point, V01 versus VS, we already have an expression, is minus 0.77. And as I said, if you build a common source amplifier, the gain also is minus 8 here. So both the amplifiers have the same gain. Okay. Let's look at the frequency response. That's where the advantages of this particular stage comes with respect to this one here. So frequency response, as usual, these are the three nodes. The resistance at this node is, resistance looking right is infinite, resistance looking left is RS, so resistance is RS here. Net capacitance at this node is CGS1 of this transistor, CGD1, which gets multiplied by AV1, the gain between these two nodes here. That's at this node here. At this particular node, net resistance we've already calculated, Norton's resistance at this particular node here. The net capacitance at this node will come due to M1 and M2. And in fact, we don't even need to bother about this particular node for frequency calculation. The reason being is, you can note here that this particular node is a low impedance node. Low impedance node, why? Because you're looking into the drain, you see a large, fine. But when you look into the source, you see a small resistance here, which means that R2 will become small. And when R2 becomes small, you multiply by C2, the time constant becomes small here. Okay, and the other time constants are going to be larger than this particular one here. Okay, so this particular node will not matter that much because it's a low impedance node here. Anyway, you can calculate the capacitance. One capacitance comes from CGD1 here. This capacitance between these two nodes, and that goes 1 minus 1 by AV1. The other one is the capacitance here, CGS2 here. The third one is CDB1, drain to body capacitance here, between drain and body, which is connected to ground here. And the last one is source to body here. This is the source, and body of this particular transistor is also connected to ground. So between source and body, there's a capacitance here, CSV2. So all you have to do is understand all the capacitances in M1 and M2 and add them up. Similarly, at this node, capacitance is CGD between gate and drain. There's no Miller's effect. You're not applying an input here. This is ground, CGD. Add between drain and body. Body is connected to ground. There's a capacitance here. And R3 is nothing but RD here. So all you need to do is sum up all these time constants and calculate the 3 dB frequency. Okay. And the node which will matter the most is this one. Will have a substantial value. And this one, if there is a large RS here. If the RS is negligible, then this one also becomes a low impedance node. This will not contribute, and the only node which will contribute is this one. Okay, so let's take an example. And so there are a lot of things here where we are trying to compare a common source amplifier and a cascode amplifier here. Okay, so let's first look at the common source here. This part here. Common source, this node is there and this node is there. And both of them we are driving through 80K here. They are biased at the same currents. The sizes of the transistors are the same. Supply voltages are the same. So everything is the same. They have the same gain. So let's look at this one. The net resistance at this node is 80K. The net capacitance is 4.4 femtofarad. The net resistance at this particular node is RS, which is 80K here. The net capacitance at this particular node is 7.6 femtofarad here. Note that CGD is getting multiplied by the gain of this particular amplifier, which is around 8 here. Okay, so this is the capacitance that you get here. And you sum these up, the two time constants, and you get a 3 dB frequency, which is 166 megahertz. Now you come to this amplifier. At this node, note that the net capacitance is 4.8 femtofarad. Note that it is smaller than this one here. This one is 7.6 because it's getting multiplied by the full gain, and this one is getting multiplied by only the gain between these 2 points, which is less than 1 here. So this is 4.8 femtofarad. Then we calculate at this particular node here and at this node here, and we sum it up, we get 183 megahertz here. Not a great improvement over this one. And the reason being is that we don't have a great improvement. The reason being is that we are building an amplifier with a very low gain. This amplifier has a gain of 8, And this also has a gain of 8. And when you have an 8, gain of 8, this is not getting multiplied by a large factor. So Miller's effect is not very prominent. Okay? It's not very prominent. And therefore, if you minimize it also, you don't see much difference between the two amplifiers in terms of frequency response. Let me build a larger gain amplifier here. Now here what I did was I put a larger resistor here. Now the gain of this amplifier is larger. Okay? Gain of this amplifier is larger. And we do a comparison, do the same thing again between this amplifier and this amplifier. This one has a 3 dB of 5 megahertz. This one 3 dB has a 12.8 megahertz. Now you can see that this one is at least twice as fast as this one. Okay? And therefore, as you build up more and more gain, you will see that this stage increasingly outperforms this particular one. Note the difference between these two. The net capacitance at this node, because it's getting multiplied by a larger gain now, gain which is 36, the net capacitance is 19 femtofarad at this node. The net capacitance at this node is only 4.8 femtofarad. Why? Because the gain between these 2 points remains small. The gain between here and here is again 36.4 between the input node and the output node. But the gain between input and this internal node remains less than 1. And therefore, the capacitance at this node is only 4.8 femtofarad, while the capacitance at this node is 19 femtofarad. Now, if I design an amplifier with a gain of 200, you can imagine that this one will become really large. This one will become really large, while this one will remain the same. And therefore, there'll be a big difference between the frequency response of these two amplifiers. Okay? So, what it is showing you then is that you have a cascode amplifier, which gives you the same gain as this particular one, doesn't suffer from Miller's effect, and therefore has a superior frequency response. The only drawback of this particular stage, as I've said, I'm not going into the details here, is in the voltage swing. For example, if I look at this one, I have to keep only transistor, this one M1 into saturation, while when I look down, I have to keep M1, M2, and I have to keep M1, both of them in saturation. So swing is what suffers here, as compared to this one. Okay. All right. So if we think about now our MOS amplifier, this is our simplest MOS amplifier with a resistive load here. Now we know the problems with this particular stage, which is that the gain of this particular stage is low unless you make RD very large. And if you make RD very large, it becomes difficult to implement. So the solution to this one was, we saw, replace RD by a transistor. Right? So this is a better amplifier where you replace RD by a transistor, and now you can get large gain without requiring a very large value of resistor here. All right. Now this one has a problem. If you want to build further gain, you could do this one. As I said, instead of one single PMOS, you could add 2 PMOSs here, and therefore you can build even larger gain here. Because the gain depends on the net resistance at this particular node here. And resistance looking down is R01, resistance looking up becomes very large here. And so this stage can potentially offer you twice the gain as this particular stage. All right. So you could go from here to a common source with an active stage. You could stack 2 of them to get even higher gain here. The other one is, instead of building this amplifier, we could build a cascode amplifier. We just saw cascode amplifier, which will give you the same gain as this one, but will give you better frequency response. Now, again, this particular amplifier, if you want to build very high gain, you would require a large value of RD, right? And therefore, that becomes difficult. So what should you do to RD? Replace it by a PMOS. So you can get an amplifier stage which looks like this. What did we do? Same stage, cascode stage. Instead of RD, we put a PMOS load here, right? So you can see a clear analogy between going from here to here as compared to going from here to here. So you can build an amplifier like this. The advantage of this amplifier will be high gain and without requiring a large resistor, and at the same time a superior frequency response. Now if you want even larger gain, what should you do? Add 1 more PMOS transistor, and therefore you can go here, right? So at this stage you add 1 more PMOS transistor here. So this will give you a very high gain, right? A very, very high gain here. In fact, if you calculate the gain will be much, much larger than this one, and will also give you a superior frequency response. Okay, so you can have any of these. You can see here stage 1, 2, 3, 4, 5, 6. These are the different possibilities that you get here. So this one will be the highest gain. We'll have good frequency response because of absence of Miller's effect. The only problem with this one is now you have to keep, when you look for the positive swing, you have to keep both of them in saturation. For the negative swing, you have to keep both of them also in saturation. So swing is what gets compromised. Okay. So this is the different options that we have available to us if you want to build a gain stage. If you want to build gain, then you could use either the simplest one here, you could use this one, you could use this one as well, you could use this one as well. Depending on the requirement, depending on the application, the amount of gain that you require, any one of these four could be useful for you. Okay. On the other, okay, so this is what we call as a CS common source amplifier with a resistive load. This is called common source with an active load. This is called common source with a cascode load. Which is the load part here? Note that this is M1 is a driver. Anything above V0 is the load here. And why are we calling it cascode? Why is the load being called cascode? See, the word cascode is used anytime the drain of a transistor is connected to the gate. We call that connection as a cascode connection here. So here, if you look at the drain of M3 is connected to the source of M2. So this is a cascode load here. This connection that you see here, where drain and source are connected together of transistor, that's a cascode connection. So we call this as a cascode load. So this is a common source amplifier with a cascode load. Now note here, this is a cascode amplifier with a resistive load. The driver, this is the driver here. This is where you are putting the signal here. So this is a driver. The load is, as I said, anything above V0. So it's a resistive load. This one is a cascode with an active load, single PMOS transistor. And this one is a cascode with a cascode load. Cascode amplifier, and the load is also a cascode load. Okay. So these are all the different possibilities. And each one of these amplifiers, this may look complicated to you, but with the two results that I gave you, if you want to gain at this particular point, all that you do is build a Norton's equivalent at this point. And the two results that I gave you, using those two results, you can very quickly, let me tell you, within 5 minutes, you can have an answer. Within 5 minutes, you can have an answer of what is the gain at this point. Similarly, within 5 minutes, you can have an answer what is the gain at this point or a gain at this point. With those two results, once you memorize, all you have to do is build a Norton's equivalent. That's it. Okay. All right. So this is all common source amplifier along with common gate stage incorporated into it. The next stage is, all right. The next stage is a common drain amplifier, which is a counterpart of common collector amplifier. And let's quickly go through the common drain amplifier then. The motivation for this is we want an amplifier with a low output resistance here. And we know that when you look into the source of an amplifier, you see a small resistance. And therefore, the idea is why not apply input to the gate and take output at the source end. Okay, so that's the motivation for building this particular amplifier here. So apply input here and take output at this particular point, and the output resistance then is going to be small here. So exactly the same thing, whatever we did for common emitter, I'm going to do the same thing for common drain amplifier. Sorry, for the common collector, I'm going to do the same thing for common drain. Same small signal analysis here. Substitute the small signal model. What you get is a gain, which is GM, RS parallel R0, 1 plus GM plus GMB, RS parallel R0. Gain is less than 1, as you can see. And output resistance is RS. You can get it from here, or you could get it from here also. Output resistance means resistance looking down, which is RS. Resistance looking into the source, which is 1 by GM plus GMB here. And normally RS will be much larger than this term, and so output resistance is simply 1 by GM plus GMB. So output resistance is low, but not as low as a common collector amplifier here. Okay, so low here means a kilo ohm. All right, so some quick results here. Most of the time, what you would find is that if the source node is connected to ground or connected to power supply here, the analysis, DC analysis becomes very straightforward. But many times what you find is that the source node is connected to a resistor and then to a supply here. Then the analysis becomes a little bit involved here. And the reason being is as follows here. So let's look at the DC analysis for a moment here. So our bias voltage is here, V bias, and AC source will short it out. So V bias is equal to, if we apply KVL, VGS here, plus the drain current which is flowing here, IDSQRS, plus whatever is the supply voltage here, VSS. So that's the equation that we get from applying KVL in this input loop here. IDS we know is beta by 2, VGS minus threshold voltage square. We'll not bother about this particular term here. In DC analysis, this is small, so we'll ignore it. Now, the trouble comes is the source here is at some voltage, and the body, remember, is connected to the most negative point, which is minus 3.3. And therefore, I have a voltage between source and body, which means that the threshold voltage is given by this expression here. Threshold voltage is zero bias threshold voltage, body parameter here, 2 phi f and all that. So now what I have to do is I have to solve these three equations simultaneously in order to arrive at what is the drain current flowing in my circuit, right? So I have this equation, I have this equation, and I have this equation. All three equations I have to solve simultaneously to arrive at what is the drain to source current here. And that is what makes it a little bit involved. So typically what you do is, in these cases, what you do is you, for a moment, ignore the body effect and say my threshold voltage is zero bias threshold voltage, which is, let's say, 1 volt. Okay, 1 volt here. And so you have 1 volt here. What you can do is then you can take IDSQ and substitute it here, and you get a quadratic equation in VGS. Solve the quadratic equation, and you get a value of VGS. And once you get a value of VGS, you get a value of current also, right? That's the first iteration. Now, once you solve all of that, you get a value of source voltage also. And therefore, you know the source to body voltage, because body is at 3.3. So now in the next iteration, you can calculate a better value of VTHN. So a new value of VTHN comes in, and then you do this again once more, and you calculate it once more, and you get another improved value of VGSQ and IDSQ, and 3-4 iterations, and it will converge. So that's why this is easy to done if you have a computer at your disposal. Otherwise, doing it on paper and pen, 1 iteration, 2 iterations, and 3 iterations can become a little bit boring here. Conceptually it's simple, but you have to repeat it 2-3 times here. Okay, there's no other alternative but do this here. Or otherwise, you can think of substituting it here at VTHN that you see here, substituting it here, substituting it, getting in one big equation, and you can try and solve it here. All right. In exams, most of the time, what we'll do is it will directly give you the current. What is the current at which it is biased? Because we don't want you to spend time 10-15 minutes simply doing 1 and 2nd and 3rd iterations. It doesn't add any value. But you have to know what the procedure is. Okay, you don't have to spend too much time doing this stuff. All right. So based on that, as you can see here, we end up calculating the bias point. For this value, the bias point is 25 microamperes. Source to body voltage is 3.3. Note the threshold voltage is 1.8. The zero bias threshold voltage is 1. The actual threshold voltage is 1.8. So it's quite different, and therefore you cannot ignore it. And the rest of the things that then one can determine here. Once you do the DC analysis, you can, using the expressions, get GM, GMB, R0. It's important that you remember all the formulas and determine all of this here. Then we plug in into our expression, we get voltage gain, which is 0.8, and we get output resistance, which is around 8K here. So this is the gain and output resistance of this common drain amplifier here. So note that the gain is significantly less than 1 here in this case. Okay, and this is 8K here. All right, the other one is this amplifier, like a common collector amplifier, is a highly linear amplifier. If you look at this particular one, AV, so V0 is very close to V in. Whatever V in you apply, V0 is equal to V in here, and that's a highly linear relationship. And this is what we find in practice, that if I apply a sinusoid here, note that I've applied almost like a 3-volt sinusoid. 3-volt sinusoid here, and so I'm getting close to, input is 3.6 and the output is 3 volt. So it's almost like rail to rail swing here, and distortion note here is less than 2%. So it's a highly linear amplifier, and So that's the other advantage of it. So it offers you low output resistance and it's a very linear amplifier. Now, before I go to the next one, what is the drawback of this amplifier? Common collector. Anybody recalls what was the drawback? It's very good output resistance, very low output resistance, highly linear. What would be the drawback? What will be the drawback for this amplifier? The drawback comes from the, well, people have forgotten. Common collector, emitter follower. The drawback comes from the swing. The swing, you'll see why the drawback is coming. So let's look at the output voltage here. As usual, at the output voltage here, we have this diagram which tells us how high my sinusoidal voltage can go, how low it can go. On the lower side, we have VSS. On the upper side, we have VDD. We have to keep the transistor in saturation, so we have VSAT1, the saturation voltage here. So if I bias it, let's say at around 0 volt here. So let's say V0 is 0 at this point, and then we know if V0 DC is 0, and let's say saturation voltage is 0.5, then we know that the output maximum output voltage swing can be 3.3 minus around 0.5, okay, which is around 2.9. And lower side is not causing any limitation here. So that's coming from keeping the transistors into saturation region. What is the other one? What are the other constraints on swing? I will not bother about distortion because we said it's a highly linear amplifier here. So we'll not bother about distortion. What is the other thing that I need to bother? Swing. Where are the other limitations that come from swing, that affect swing? The current. The fact that the moment I put a load here, then I must have sufficient current in my system to attain that particular swing here. Okay. All right. So swing, which is limited by output current here. And how do we do this? Well, we say, well, suppose the swing voltage swing you require is V0M, and note that the limitation comes from negative swing here. So you require a current IL, which goes like this here, and I must have enough current here to supply this current here. So this current must be greater than or equal to IL, and therefore the IL that you see here is V0M by RL, which is this current, and the current which is going down is V0M and VSS here divided by RS here. Note that we are talking about negative swing here. So the voltage is minus V0M, the voltage is minus whatever voltage VSS. So that's the net current which is going down, and this current must be larger than this current, and therefore we have this constraint here. And from there, then we get that maximum swing that you can get is VSS by RS into RS parallel RL here. Okay. In all of this, we are assuming that the output voltage, DC value of output voltage is 0. Okay. The reason being that DC value of output voltage is 0 is that I don't want any DC current flowing into my load here. All right. I've not used a capacitor here, a coupling capacitor, because we would be interested in using this amplifier on an IC, let's say, and therefore we've avoided any coupling capacitors here. All right. And therefore, the output DC value is 0, and the net voltage then at this particular node is, we are calling it minus V0M then. So that's the value that comes in from the current point of view. So if you have a very low value of RL, then this term becomes small, and therefore the swing can get limited by the current limitation here. Okay. So we have these two limitations here. One is from this side, and the other is from the current limitation here. Okay. And we have seen earlier that this current limitation can be improved if you replace RS and replace it by a current source. Okay. So this one makes it, same calculation is being done here. So this says that the swing is simply equal to I by S times RL. Okay. So this is more like exactly the same things that we have done with common collector, same things being repeated here with common drain here. Okay. So I have an example here which tells, so here, if you go back here, this is a current source. Current source is being implemented by a transistor M2, biased in saturation region here. Now note a couple of things here. If I have RL equal to 1K and I want to develop a swing of around 3 volt, okay, 3 volts around in RL equal to 1K. So the previous one is telling you now, if you want to develop a swing of 3 volt, RL equal to 1K, it tells you that the bias current must be 3 divided by RL around 3 milliamperes. Okay, so that's why we are biasing it a little above, because it says the current should be greater than 3 milliamperes, so we're biasing it at around 3.3. Now, when you bias it at that large current, you have to use a large size. Because if I don't use large size, then what will happen is I will require a very large gate to source voltage. In fact, the maximum gate to source voltage that is available to you is the supply voltage 3.3. And then it will become difficult for you to even bias it at that large current here. Alright, so even in this case, if you note, I have to bias it at 3.3, and note this, I have taken 200 by 1 size, very large size here. Even then, I require a gate to source voltage which is 2.4 volt. 2.4 volts is needed to just bias my M1 at 3.3 milliamperes here. Okay, we are assuming that V0 value is 0 here. DC value is 0 here. So 2.4 volts is needed. Now you can easily do the calculation, and suppose you had biased it at 2 by 1, you would have seen that the gate to source voltage required would have exceeded the supply voltage here. Not possible. Okay, so that's one reason why you have to make the sizes large here to manage this VGS1. And similarly, VGS2 is larger here. Why is the difference between the two? Same current is flowing through M1 and M2, bias current. Sizes are the same. Here I require a gate to source voltage which is 2.4, and here I require 1.5. Why the difference between the two? Huh? The threshold voltage. Threshold voltage of M1, because its body is connected to 3.3, so source to body voltage is there. Threshold voltage of M1 is much higher, and body of this one is connected to 3.3. So source and body are both connected to 3.3, and therefore threshold voltage is 1, and threshold voltage here will most likely be 1.8 or 2. So threshold voltage itself becomes very high. Okay, and that's why you require a very large voltage here. Now you can see, after doing all this, you can see, okay, so I can do this. AV is 0.79, R0 is 74 ohms, and in this case, we have to keep M1 into saturation, we have to keep M2 into saturation, and we can find out what is the V0 max 1 and V0 max 2 here, the two values here. This comes out to be 2.72, and this one will come out to be the same. It's a symmetrical device here. You can see a problem at this stage here. See, this is 2.4. This is 2.4. This is 0, and your input is coming from here. Now, where is this input actually going to come from? Note that this amplifier has a gain equal to 1, right? A gain less than 1. So, this amplifier you'll be using in series with other amplifiers, right? So, before this, this amplifier, as I said, is going to be driven by a previous amplifier, a gain stage. What is a good gain stage? You see here. So actually, you're not going to use a function generator or something like that to drive it. The driver for this is going to be a previous stage here. And previous stage I've shown you is something like this, a common source stage with an active load. So which means that what is the highest value this node can take? V0. What is the highest value that it can take? How large can it go on the positive side? Obviously, on the positive side, V0 can go at the most to 3.3. Actually, 3.3 minus the saturation voltage drop, right? So now go back to this diagram here. The maximum voltage that this node can go is 3.3. And V bias 1 is 2.4. So what is the largest value of V in that you can apply? If this is 2.4, right? And as I said, the maximum value of this particular node, because note that these two together is nothing but coming from the previous stage here. The two together is nothing but this voltage here, okay? Which is this point here. So if you go back and ask yourself, if this is 2.4 and the maximum voltage at this node can go to 3.3, so what is the highest value of Vin that I can apply? 3.3 minus 2.4, which is what? Roughly 1 volt. So if Vin is 1 volt, what is the maximum value of V0 that you can get? Note the gain of this amplifier is 0.8. So the maximum value of V0 that you can get is 0.8. So a trouble is coming because normally you're going to drive this particular stage from a previous stage. And previous stage, this voltage is limited to 3.3. And if this is limited to 3.3, the maximum input that you can apply is only 1. And therefore, the maximum swing that you can get is only 0.8. This is the trouble with this amplifier. Now, how do I get a larger swing, V0? Well, you get a larger swing by making V bias smaller. How do you make V bias smaller? For the same current, how do you make V bias smaller? You'll have to increase the size even more. From 200 by 1, maybe you'll have to make 500 by 1, but you'll not gain much. So a major problem with this amplifier is that although looking at it from the output side, you're seeing that, well, I can get a reasonable swing. But note that I have to apply a large enough voltage to get that swing, input from the input side. And the limitation is coming from the input side. The limitation of this amplifier is not coming from the output side here, that this voltage cannot go to 3.3 or cannot go here. The limitation is coming that I need a signal at the input side which is large enough. And that is a problem. How do I develop a large enough signal here? That becomes a problem here. And this is a major limitation of this one. All right, so we'll discuss this tomorrow.